So to make the rocket go up, we use Newton's three laws. The first law is when the rocket will remain on the launch pad until an imbalanced force is exerted on it, propelling the rocket upward. So the second law is the amount of force depends upon how much air is pumped inside the rocket. You can increase the force further by adding a small amount of water, which increases the mass expelled by the air pressure in the rocket. The third law is finally the action force of the air and the water as it rushes out of the nozzle creates an equal and opposite reaction force propelling the rocket upward. So on our rocket, the purpose of the fins was to add surface area to the back of the rocket, which helps keep the nose of the rocket pointed into the wind. So in order for the rocket to fly in a stable fashion, the center of mass of the rocket must be in front of the center of pressure. So by adding clay in the nose cone section, it will help move the center of mass toward the nose of the rocket. The nose cone helps reduce air drag by streamlining the air as it flows past the surface of the rocket.
Based on a simple physics concept in which water is forced out of the bottom of the rocket by air pressure, and in doing so exerts an upward force pushing up on the rocket, per Newton's third law. When the rocket finally launches, the water starts to exit at high speed due to the pressure inside the rocket body forcing the water out. As the water exits, it accelerates downward due to a large downward force caused by the internal pressure. By Newton's third law, there is also an equal and opposite force pushing upward on the rocket, causing it to accelerate upward. If the rocket took 1 second to travel to the final height would be 5 meters. But if the rocket took 5 seconds to travel to the final height would be 123 meters. To estimate our rocket's height, we used kinematics. To save our own time, we estimated the time for how long the rocket will take to reach the final height. For our data, we measured 10 different time periods.
As you can see, our rocket launched on our first attempt. This is because our nose cone on the rocket reduced air resistance as it flew through the air. During the flight, it kept a vertical angle because of the weight of the rocket was compared to the fuel of the rocket. Now we needed to measure the actual height. The two variables we know were the acceleration due to gravity, which is negative 9.8, and the time. We used a stopwatch to calculate the time, which was 5.7 seconds when the rocket reached the ground. Then we had to divide that number by 2 in order to find the maximum height, which was 2.85 seconds. The second step is finding the initial velocity. We divided acceleration by time to find the initial velocity, which was 27.93 meters per second. Finally, we have all the variables for calculating the height, so we used the change in x kinematics equation and found that the maximum height of the rocket was 33.83 meters.
So the reason why ours did so well, thankfully, was that we managed to put the center of mass above the center of pressure by using a piece of clay under the cone. This kept it more stable. As you could see with our flight path, it was generally quite straight, and our fins were short and sturdy rather than long and curved, which provided more stability as well. We also did not have any leaks. If we did have any leaks, we wouldn't have been able to launch the bottle, and we also managed to fit the nozzle in perfectly, which helped the launch.